Hello, good doing good, yeah. Welcome to this explainer. Look, today we're not just, memorizing textbook science. We are literally stepping into the shoes of the greatest detectives in human history. We're going to unravel a thrilling scientific detective story, one that actually took over 2,000 years to fully solve. We're talking about the complete structure of the atom. Trust me, we are going to have an absolute blast unlocking the ultimate secrets of matter today.
Okay, let's dive into this. I want you to seriously look around you right now. Like, take a look at your phone, the desk you're sitting at, even your own hands. What is all of this stuff actually made of? If you keep zooming in, past the skin, past the cells, way past the molecules, what is the fundamental building block of the entire universe?
Well, the story starts way back around 500 BC. Over in India, Maharishi Kanad proposed that absolutely everything is made of tiny, indivisible particles he called parmanu. Around the exact same time in Greece, Democritus called them atoms, which literally means indivisible. Fast forward a bit to the year 1800, and John Dalton's atomic theory comes along and confirms this whole idea. So for thousands of years, humanity just believed the atom was the absolute smallest thing in existence. You simply couldn't break it. But then, between 1897 and 1932, a massive shockwave hit the scientific community. The atom was cracked open. Scientists realized, to their absolute shock, that the atom was actually divisible, containing even smaller pieces hidden inside.
So, let's look at our lineup of subatomic suspects. We essentially have three main characters discovered by brilliant minds like Thomson, Rutherford, and Chadwick. First, the proton. It's positively charged and locks safely inside the nucleus at the very center. Protons are kind of like your true, loyal friends. They just stay with you forever. Then there's the neutron, which is also just chilling in the nucleus, totally neutral, zero charge. But then we have the electron, negatively charged and constantly revolving on the outside. Electrons are, well, completely disloyal. They're always running around and can even jump ship to other atoms entirely.
Section 1. The first detective, J.J. Thomson's sweet mistake.
J.J. Thomson was an absolute genius. He actually discovered the electron. But once he found this tiny negative particle, he had to try and guess what the entire inside of an atom actually looked like. And to explain his vision to the world, he used a brilliantly simple, relatable analogy. Think of a watermelon. Thomson suggested that the atom is like a giant sphere of positive charge. That would be the red edible part of the watermelon spread out everywhere. And the negative electrons? They're basically like the black seeds, just studded randomly inside that red flesh. So the total positive charge perfectly equal the negative charge, making the whole atom completely neutral. It sounded delicious, honestly, and it made perfect sense at the time.
Section 2. The Master Detective, Ernest Rutherford's Shocking Gold Foil Experiment.
Now, as you know, science is all about testing ideas. Ernest Rutherford was actually Thomson's student, and he decided to put his teacher's watermelon model to the ultimate test. He set up the now legendary gold foil experiment. Basically, he took heavy, fast-moving, positively charged alpha particles and shot them like microscopic bullets. His target? An ultra-thin sheet of gold foil. And why gold? Well, because gold is highly malleable. He beat it down until it was incredibly thin, literally only about 1,000 atoms thick. He placed a fluorescent screen behind it so he could see a little flash of light wherever a particle landed. He fully expected these heavy positive bullets to just blast straight through Thomson's soft, fleshy watermelon positive atom. But the results? Absolutely mind-blowing. First off, 99% of the particles pass straight through without a single issue. This meant the atom isn't a solid watermelon at all. It's practically entirely empty space. But then, the unthinkable happened. While a few particles deflected slightly, exactly 1 out of every 12,000 particles hit the foil and rebounded a full 180 degrees straight back at Rutherford. Imagine riding a bicycle at top speed and slamming into a massive parked truck. You'd bounce straight back. Rutherford realized right then that something incredibly heavy and positively charged had to be hiding at the very dead center of the atom.
He called this incredibly dense center the nucleus. So, to put that into perspective, think about this number right here, 100,000. The nucleus is 100,000 times smaller than the atom itself. If you want to really picture this, imagine the entire atom is the size of a giant room. The nucleus, holding all that positive charge and heavy mass, it would be the size of a single grain of salt sitting right in the exact center of that room. It's almost unbelievably tiny, yet it holds all the power.
Based on this, Rutherford proposed a planetary model, with negative electrons orbiting the positive nucleus, kind of like planets orbiting the sun. But a massive scientific flaw quickly popped up. Another brilliant scientist named Maxwell had a well-proven theory. Any charged particle that accelerates, like an electron constantly changing direction in the circular orbit, absolutely must lose energy. So, if the negative electron is constantly losing energy and the positive nucleus is constantly pulling it inward, why doesn't it just, crash?
Well, according to the strict physics of Rutherford's model, it absolutely should crash. In fact, scientists crunched the numbers and calculated that an electron would spiral into the nucleus and self-destruct in 0.0000001 seconds. Think about that. If this model was entirely correct, every single atom in the universe would collapse practically instantly. The mere fact that you and I currently exist proves that something major was missing from this picture.
Section 3. Bohr's brilliant fix, the era of discrete energy levels.
Enter Niels Bohr, the absolute hero who saved the atom. He looked at Rutherford's model and essentially said, okay, the basics are right, but we desperately need some strict cosmic traffic rules here. So he introduced the concept of discrete orbits. He declared that electrons can't just fly around wherever they want. No way. They have to stay in fixed circular paths, or shells, which he named K, L, M, and N. And here is the real genius of his fix. As long as an electron stays in its designated lane, it mathematically cannot lose or gain energy. By establishing these safe zones, Bohr proved exactly why the atom remains perfectly, beautifully stable.
Section 4. The rules of the game, mastering electronic configuration.
So now that we have a stable picture of the atom, how exactly do we pack the electrons inside? Well, before we do that, we have to establish identity. The atomic number, which is represented by the letter Z, is the total number of protons in the nucleus. Remember how we said earlier that electrons are disloyal and can just run away? Protons never leave. If you have 8 protons, you are always an oxygen atom, period. The atomic number is basically the atom's true, unhackable identity card.
Okay, so how many electrons can actually fit into Bohr's shells? Bohr, teaming up with another scientist named Bury, gave us this golden mathematical rule. 2n squared. The n here is just the shell number. This incredibly simple formula unlocks the maximum capacity of any shell in the atom.
Let's break down these rules really quickly. Step 1. Use 2n squared. The first shell, K, can hold a maximum of 2 electrons. The second shell, L, holds 8. The third, M, holds 18, and the N shell holds 32. But wait, step 2 is arguably the most vital rule of all. The outermost shell of an atom can never hold more than 8 electrons, period. Even if that specific shell has the capacity for, say, 18 electrons, if it happens to be the currently outermost layer, the universe steps in and caps it at a strict maximum of 8.
Let's actually build some atoms and see how this works in reality. Take oxygen. It has 8 protons and thus 8 electrons. It fills 2 in the K shell, and the remaining 6 go straight into the L shell. Super easy. Silicon has 14. That's 2, then 8, leaving exactly 4 for the M shell. But look very closely at calcium, which has 20 electrons. It goes 2, then 8, which equals 10. So we have 10 left. Now, the M shell can hold up to 18, right? So why don't we just dump all 10 into the M shell? Well, actually, scratch that. Because of rule number 2. If we put 10 in the M shell, it becomes the outermost shell. And remember, the outermost shell cannot have more than 8. So calcium plays it safe, puts 8 in the M shell, and neatly drops its last 2 electrons into a brand new N shell. Brilliant, isn't it?
Section 5. The ultimate goal, the octet rule and chemical peace.
And now we reach the grand finale. Why do atoms behave the way they do? Well, everything in chemistry really comes down to that outermost shell, which we call the valence shell. The octet rule states that atoms reach a state of absolute monk-like peace and perfect stability only when they have exactly 8 valence electrons. Elements like neon and argon are literally called noble gases because they naturally already have 8 electrons in their outer shell. They have achieved chemical nirvana. They are completely peaceful, completely satisfied, and they don't react with anyone.
But here's the catch. Most atoms do not have 8 valence electrons, which leaves us with a pretty thrilling cliffhanger. If almost every single atom in the entire universe is just desperately trying to reach that perfect number of 8 valence electrons to find peace, what chaotic, violent, and incredible things will they do to steal, share, or give away electrons just to get there? That chaos, my friends, is exactly what we call chemical reactions and bonding, and it is the very thing that creates the entire living, breathing world around us. Thank you so much for tuning in, Guddu and Guddia, to this explainer. Stay curious, keep questioning, and I will catch you in the next one.